actually worn a mic like this. They are quite cool, but it feels like I'm working in like a customer support center. How can I help you today? Today I will be presenting a paper I've written with my supervisor, Bob Sturm, at KDH in Stockholm. And it's about creating virtual instruments from unstructured instrument recordings. We know that we can create, we can record every key of a piano and then make a sampler instrument. But if we don't have access to a structured recording like this, we still might want to make some virtual instruments. Why? We want to edit existing recording, and we also want to repurpose past timbre in new music. So I will start with the demo today, and then you can all check out. So using our method, okay, so let's first listen to this recording, this beautiful 16 seconds of saxophone. So using only those 16 seconds, we fit a clone, and we then use this clone to edit the dynamics. So here we made it louder. And quieter. And I'm already anticipating a question about loudness. Really? We've already invented the gain knob. Why do we need the neural networks to change loudness? So here we're also changing the timbre in a way that's kind of consistent with the louder volume. We can also go a little bit more extreme. And then very, very quiet. We can also edit pitch. And pitch down. And we can also use our clone in an application called timbre transfer, where we take an excerpt here from a different saxophone. And re-render it with the timbre of our target recording. All right, so how do we do this? We start from DDSP. I think you're a bit tired of seeing this diagram by now, but I'll go through it quickly. So the big idea is let's integrate DSP components into neural network architectures. And in this instance, more specifically, we're using a neural net to control a harmonic plus noise synth. And Gael kind of presented this really nicely, this idea of hybrid deep learning. The way I summarize it is don't try to learn what you already know. And we know that we can synthesize some instruments with a mix of harmonic sinusoidals and a filtered noise. So let's use that. The problem is that the DDSP paper claims that you need about 10 minutes of audio. And those, as someone who worked a lot with DDSP when it came out, I found out very quickly that it's kind of hard to find 10-minute solo instrument recordings online. But we thought we would ignore the advice that DDSP gives about these 10 minutes, and we tried to just train a DDSP model, a very simple DDSP model on 32 seconds of saxophone. And what we discovered was interesting. So here's, I won't play you the training data, but here's an unseen excerpt that we're trying to resynthesize from only a F0 and loudness contour. So this is the excerpt. And here's the resynthesis. All right, so what's that? Did you hear the wobble? So the wobble, it actually lines up perfectly with something that happens in this ground truth signal. So there's a breath there. And so when there's a breath, the loudness contour tells you play something. But the F0 contour is all over the place, so we hear this wobble effect. And this happens whenever we have key presses, breaths, page turns, more like transient sounds, and all types of like noisy, non-pitched sounds. So, right, remember the motto of hybrid deep learning, don't try to learn what you already know. Why don't we condition with the F0 confidence contour? That tells you like this part should not be pitched because we don't have any confidence about the pitch. So we just use the confidence contour that's outputted by our pitch tracking algorithm, and we just feed that in, and it's much less noticeable. There's still a problem. So if we compare the ground truth here with the resynthesis, all right, so it sounds a lot roomier. Unfortunately, we're in a room that has quite a lot of reverb. So you're probably not going to notice it, but there is like this trailing reverb that's all throughout the recordings. And what we think is going on is that the instrument sound is entangled with the reverb impulse response. So it's too free in a way. So what do? We need to put it in impulse response prison by constraining it, and the way we constrain it is we use an old trick of combining a short, completely free impulse response for the Euler reflections, and then using a filtered noise to model the dense reverberation. And so using this approach, we now have a resynthesis that's much closer to our ground truth. Let's listen back to our ground truth quickly. Okay, good. Can we go lower than 32 seconds? Here's what happens if we try to train it on 16 seconds. All right. In my ears, maybe not in this room, but if I listen to this with headphones, it has very poor naturalness, and it has relatively poor similarity to the target. In order to go lower in training data duration, we are going to use transfer learning. So we really like this paper from the speech community, which is about neural voice cloning. And they use a multi-speaker model that's trained on many speakers, and then they simply adapt this model to the target speaker. Similarly, we can pre-train a multi-instrument model on many instruments and then adapt it to the cloning target instrument. So if we have seen many saxophones, we can then give pretty good guesses of what is missing here. So I let just this analogy sink in a little bit. All right, good. So let's apply the speaker adaptation technique. And the way we do it, we just slap on a latent vector here. You see there's no encoder. So, and the reason we have no encoder is we are lazy. We do not want to mess around with additional hyperparameters. What should be what structure should the encoder have? We don't care. We just slap on an encoder and we learn this Z in conjunction with the rest of the network. So we treat these latent vectors as model weights, exactly as we do the reverb, only that they are unique to each recording. And if we do this, we can sort of get down to, so it's a bit quieter now. We can go even crazier. We can go 4 seconds. And here's where things kind of start to get a little bit weird. And let's compare that to our ground truth. Right, and remember, this is a test excerpt. This has not been seen during training. But one consistent artifact that we find with this method is that the resynthesis always sounds a little bit roomier. Basically, there's sort of a blur on the results. All right, what if the cloning target is of an instrument type not seen during pre-training? I don't know what this is. And let's pretend like our network doesn't know what a saxophone is. So we pre-train on 8 hours of wind instruments, but no saxophone. And then we just simply try to tune, to adapt our model on only 16 seconds of saxophone data. And it sounds like this. So in summary, we've extended DDSP with F0 confidence conditioning. We use a 2-part reverb design, and we use transfer learning across both instruments and instrument types. And this allows us to clone instruments from less target audio. All right, this is a bit insane, but you could, I think, if you were to kind of combine what we've done here with what you've done yesterday, you could perhaps do simultaneous transcription and instrument cloning. There's a lot of clues in these references that tells you that this might be possible. So the problem, right, we are gifted with the ability to estimate pitch if it's a monophonic signal. We can do this really well, but we're sort of bad at doing it polyphonically, unless it's from like a source that we know really well, like a piano or something. But what if we could initialize a multi-instrument model, just initialize a random Z and initialize a blank transcription, and then just try to find whatever Z and whatever transcription will generate the target audio. Maybe it won't work, or maybe it will work. We'll see. That's all I had for you today. You can check out lots of more audio examples, some code. There's like a dusty Jupyter notebook from last year, all kinds of fun things if you go to this QR code, and I'll be happy to answer any questions.
Do we have any questions from the audience? Sure. Okay, in that case, I have a question. Could you go back to the slide where you show your adapted DDSP implementation? It was maybe 5 slides.
So is
that
it
one done? Yeah.
This one? Yeah?
Yeah. From reading the paper, it wasn't very clear to me how you compute the embeddings set. I think you mentioned you trained them separately.
Right. Sorry for being very unclear in the paper. So I have it now kind of, this diagram might be a bit ambiguous because you see I'm represented conditioning in kind of the same way as I've represented model weights. But that's because I don't really think that there's a categorical difference. because you could, so what we do here, to get our Z, we initialize it randomly, and then in order to optimize, to decrease the loss, we are tuning Z, just like a model parameter. So one way to look at it is that it's not really a conditioning feature, but more of a model weight. The weird thing is that it's a model weight that's unique to every recording. So think of it as like there's a shared part, which is shared across recording, which is the blue part, and then you have the beige part, which is specific to each recording. Does that make sense?
Yes, thank you.
Perfect.
Yeah, we have a question here.
Hi, and thanks for the great presentation. I had a question regarding this exact same embedding, and I was wondering if you considered at some point using adaptive instance normalization, such as in StyleGAN, to kind of share styles in between instruments.
No. I have not heard of that, but it sounds very interesting. So please tell me about it. Maybe after the presentation.
Yeah, we have a question in the back. Alec, maybe if you could start getting ready. Unless we need the slides then.
Hi, so for the reverb, you said that like usually if you send in less target audio, the sounds turn out to be more roomier. So basically a larger decay rate for the reverb impulse response. So does that happen even if you initialize it differently?
So yeah, that's a really good question. Yes, we desperately try to just kind of initialize it with a very, very sparse, like very short reverb. But we think that the problem is that, so if you only have 4 seconds of target data, and you have an impulse response that's like 1 second, a very attractive solution is to kind of have the impulse response just be a sort of average of all the target data. So we think that's the issue. Well, okay, so that's the issue with yeah, I would say that's the main issue. Then there's a second source of roominess, which I think just has to do with a general like blurriness, since we kind of treating it as like since we are only allowing it to fine-tune the Z and reverb during cloning, we might not be able to render the finer details. So I think there's kind of 2 separate sources of roominess going on in this paper that are completely different. That's what I think, at least.
There was a paper in 2016 by Trier and McDermott on like a generative model for reverb. So maybe if you build that in, it will get easier because that takes into account natural statistics of reverb. So you'll be learning less number of parameters, and the model will not be free to learn roomier reverbs because they will be less likely.
Yeah, so that I think is a really good idea, actually. So basically it would be to have a separate generative model for reverbs, and you just fine-tune some sort of embedding for that, right?
Yeah, yeah. Exactly.
Yeah, I think that would work really well, actually.
Thank you very much.
Thank you.
Let's give Nicolas another round of applause, please.